Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list published on November 22, 2025, about 4 days ago. This paper introduces UltraFlux, a data and model co-design that finally makes native 4K, multi-aspect ratio text-to-image generation stable and high quality, consistently beating strong open-source baselines, and even matching or surpassing the proprietary Seedream 4.0 when paired with a large language model prompt refiner. The paper is titled UltraFlux, Data Model Co-Design for High-Quality Native 4K Text-to-Image Generation Across Diverse Aspect Ratios, and as we will see later, the implications for scaling diffusion transformers to real 4K are quite significant. Also, the authors shared an open GitHub repo. Inside, you'll find a Python inference script that automatically downloads UltraFlux checkpoints, runs curated prompts, and saves native 4K outputs. The README explains model variants, how to customize prompts and settings, and outlines upcoming releases for training code, evaluation tools, and the 4K dataset. On Hugging Face, you'll find UltraFlux v1 and the upgraded version 1.1 transformer weights, plus the 4K VAE and diffusers code snippets to generate native 4K multi-aspect images. Figure 1 gives a visual promise of what UltraFlux aims to deliver: sharp, photorealistic 4K images across very different aspect ratios and subjects using one model. The left side displays wide landscapes, portraits, food scenes, and close-up objects that all keep fine textures and natural lighting. The right side highlights the multi-aspect 4K1M dataset, which provides many native 4K scenes across shapes and compositions, so the model can learn to handle wide, square, and tall formats consistently. Figure 2 explains how the team curates the multi-aspect 4K1M dataset, so the model sees only clean, rich, well-described images. The top stream shows a general path that filters raw internet data by safety, 4K resolution, low-level quality, information entropy, and aesthetics, where information entropy here means how much visual detail and structure an image carries. The bottom stream shows a human-focused path that first detects character images, then applies the same quality and aesthetic checks. Both streams end with bilingual captioning, so each selected image comes with strong text descriptions in 2 languages. Table 2 summarizes quantitative 4K results and shows that UltraFlux consistently scores better than other open-source methods, with lower Fréchet inception distance and higher aesthetic and alignment metrics, which together indicate sharper, more on-prompt images. Tables 3 and 4 then compare UltraFlux to Sana at different wide and tall aspect ratios, where UltraFlux again wins across almost every score. Table 5 finally pits UltraFlux with a prompt refiner against the proprietary Seedream 4.0, showing roughly comparable fidelity but noticeably stronger image quality and alignment metrics overall. Figure 6 makes the performance gap very concrete because it shows side-by-side 4K images from each open-source model and UltraFlux for the same prompts. Across the owl portrait, the flower picture, and the mountain lake, UltraFlux keeps crisp textures, realistic lighting, and clean edges. The competing methods often look softer, noisier, or slightly distorted, especially in fine details like feathers, flower petals, and tree lines. This visual comparison supports the quantitative metrics that showed UltraFlux delivering both higher aesthetic quality and better prompt alignment at native 4K. Figure 7 explains why the resonant positional encoding keeps large images stable by aligning each frequency band so its phase closes cleanly at the training window. This figure shows 3 bandwise diagnostics across rotary bands. The left plot compares how many cycles each band completes, where the resonant version snaps messy fractional cycles into neat integers. The middle plot shows that this snapping drives the phase closure error almost to 0, while the baseline oscillates wildly. The right heat map visualizes extrapolated phase differences across positions, revealing that only the baseline accumulates large out-of-distribution phase shifts as sequences get longer. So while Figure 7 analyzed why the positional encoding stays stable at 4K, Table 11 shows how that stability translates into performance across wide aspect ratios. The table reports Fréchet inception distance, which is a realism score where lower is better, plus 3 perceptual and alignment metrics. Across 2:1, 1:2, 16:9, and 2.39:1 formats, UltraFlux consistently achieves the best or tied best scores, meaning it delivers sharper, better aligned wide format images than all open baselines. UltraFlux shows that native 4K text-to-image is really a systems problem. Data curation, positional encoding, compression, and loss design all must work together, not as isolated tweaks. The broader implication is that future high-resolution models will likely be co-designed end-to-end. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.